Thank you for having me. I would like to start simple. Gradient descent can write code better than you. I'm sorry. Now, before we get into details of who was the author of this, do you remember what gradient descent is? Show of hands. OK, we got a couple of people. So gradient descent is first derivative of a function. We call it похідна. And if you go in the direction where it descends, you can find the minimum of a function. And if the function happens to be a cost function or a loss function, you can find the minimum cost, which is really helpful if you happen to be training statistical models. Now, who of you remember this guy? No? OK. OK. We'll talk more about him. Now, why you should be listening to a guy from Netflix talking about statistical models here on a Highload? Maybe because I worked at some really impressive companies. Any people from EPAM here? Oh, well, OK. And less impressive companies? You can probably say who's the brave soul out there. And it rolled down and down and down until I ended up here. So right now, I'm one of the members of media intelligence team at Netflix. We're not trying to build general intelligence, not artificial intelligence. We're trying to answer one simple question. What's happening in the movie? We get simple tasks, and we try to solve them in the best way possible. I'll show you a couple of samples here. So we started with something that was just really basic. Imagine a movie being uploaded to Netflix, and the first thing you need to know is that a movie at all? Is that zip file containing subtitles and maybe a video file, maybe audio? And from there, we went to a little bit more complicated checks, like, is the movie playable? Are the subtitles the right subtitles? Are they in the right language? And finally, we went to some more important things, like, are there dead pixels in the picture? And eventually, since we had all the machinery built up for all these analyses, at the point of ingestion, we decided to add more information, add more analysis, so that we are actually enriching the metadata about the movie. Here are a few samples. Dead pixels. So what you see on this picture is actually, pieces of movie that don't carry any visual information. You see, the movies are being shot on the cameras, and cameras are physical objects. And physical objects have physical defects, like there could be a dust. There could be just physical damage, which means that you'll get a point that doesn't carry any visual information. And the worst thing about that is that the more you encode the movie, the more that thing grows. It just stays there all the time. It's like a cancer of video encoding. So you need to know them, preferably sooner than later. There is another interesting problem. Number of movies on Netflix is big. There is a lot of possible options for images you could create for those movies, advertising those movies. And then there is a big audience. So combining the two is like a multiplication every time. So picking the right picture to represent a particular title is a really combinatorially hard problem. So what we're trying to do is facilitate people, giving them the best options, the best shots from a movie, so they could then perform their task and come up with something like a smaller artwork, a thumbnail that helps our users pick a movie to play. And here's the UI that we use for our creatives, people who are actually making a selection, picking the right picture for a movie. Another interesting problem that we are faced with is the banner. How many of you actually opened Netflix title page? Some? All right. So you probably know there is like big advertisement of a movie, like once you land there. And that one has a certain template. So there is a part of that that is just empty. There is some text. There are some controls to play the movie. And we try to pick those images automatically as well. But they need to fulfill this template. Otherwise, it's a bad experience. So here would be a good example. But what if the object is on the other side? Then it would look like this. Finally, there is a problem of QC. So imagine an image like this. The problem is that rectangle on the right, it's actually a camera. It's a light that just got into the picture. We should be able to know about that way in advance, as sooner as possible. Another interesting problem arrives here. So this is a name of the actor being overshadowed by subtitles. To find this problem, you actually need to watch all the movies in all the possible subtitles and find the collision. It's really hard for a human. At least it costs a lot. So if you could do that with machines, that's just simpler and faster. So we talked about the problems that we have right now. How does industry solve this right now? Usually, machine learning. Usually, machine learning means a lot of data. How do people treat data? Well, you know, one measure that I like myself is by the amount of sleep that is lost over a certain problem. So here is the average breakdown. When you're in university, when you're doing a PhD, it's all about new algorithm. It's all about new statistical model, new neural net, something like that. You get your data set from, I don't know, MNIST, maybe something on the YouTube, something open sourced. And finally, when you move to the industry, you realize it's a completely different world. Like, almost any algorithm can work okay if you have enough data, if your data is okay. To be specific, it's really hard to beat random forest. And this could be a really nice joke if the original slide wouldn't look like this. So this is the slide from a guy whose name is Andrei Karpathy, whom you saw before. And he happens to be director of AI at Tesla, and he's also a PhD at Stanford. So there is some legitimacy to what he is caring about. Now, why this shift exists? Why there is a difference between what you do in academia and what you do in the industry? One of the possible answers is domain shift. So domain shift is when you train your model in one data set, but then when you move it to production, it happens to be a completely different data set. Well, this one is kind of, I was trying to simulate what automated driving could be experiencing. I hope real people doing automated driving know what the day and night is, but the idea is the same. If you train on something that is a little bit different from your actual real-world inputs, your statistical model will go to waste. In fact, neural networks are so good at finding teeny tiny differences that it's possible to convince them that something is of completely different class, even though humans don't recognize this. It's called adversarial attack. So I love this because it's so versatile in this example. The first one is just a picture from your data set. It's a washer. It's clear, right? Now, the second one is the same picture printed on a piece of paper and then pictured with the average cell phone. And it's still a washer with a reasonably high confidence. Now, the second one, the third one, is actually the first image with some specifically crafted noise, then printed and pictured. And it happens to be a safe or a washer. You know, the third one actually, safe or speaker. Washer is not even part of the picture. There are both white box and black box versions of this attack. If I know the details of the neural network, I can make it behave as if it was a gun or as if it was a panda, whatever. Now, why is this important? This is important because the way to make your statistical models robust is to actually add those examples to your data set and retrain again. That's the classical way of dealing with this kind of problem. But what does that mean for us? It actually means that your data set is not a stale thing, it's a growing thing. You are constantly adding things to it. People at Twitter had this paper several years back where they said, you know, there's actually a separate role, people who just watch the data set and make sure that the inputs are conforming to what model is expecting. Managing the data infrastructure is a big thing. Some people from a company called Google, where they do it for probably a couple of decades right now, have this problem. So what they say is that when you create a machine learning infrastructure, you also create a lot of other services that monitor your data, that create tests for your data, and that keep your data in check with whatever model is expecting. Not to mention that the model itself has to evolve and update all the time. In fact, it's so hard for them that they call it the high-interest credit card of technical debt. It's accruing. And the problem with this is that you need to have all this infrastructure, because when the model fails, it fails silently. You don't get errors, you don't get exceptions, no error codes. Your metrics start to decay a little bit, one by one. And sometimes it's not just your crucial metric. Sometimes it's your secondary metric. Sometimes it's a metric on a just longer horizon. How do you know about that? Well, you build a system like this. So machine learning is actually just a teeny tiny part of that, and everything else is taking care of, just making sure your model is doing the right thing. Now, at this point, you can think, right, at some point, I will reach that peak. I will get to the point where my model is going to be cool, it's going to be robust to all the attacks, it's going to be fine. We're all going to be good. And then we'll let go of this, whole bulky infrastructure. We'll keep the teeny tiny ML code. It's going to be fine. Yeah. So these people, Andreessen and Horowitz, they are one of the most successful venture funds in the Valley. And what they say is that essentially data keeps changing so much that it doesn't make sense to focus on that. It could be summarized in this phrase. Focusing on the data as your competitive advantage makes no sense. It just distracts you from delivering a product. So on one hand side, your data keeps evolving. Going back to our previous example about automated driving, streets get changed. Signs get changed on the streets. Sometimes you have, construction workers over there. Here, I remember streets in spring being completely different from what they were in the autumn, right? So how do we work with all this? On one hand side, the data is keeping changing, and we need it to being deprecated. On the other hand side, we need it to make our model better and better, and it's a vortex. You have to deprecate one, you have to create another one, and it keeps going in the loop. Speaking frankly, it's pretty much like doing code right now. So remember, like your test coverage is never complete. Remember, like your code is never complete and there are always some kind of bugs. Same thing about your data, which means that one point in time is okay, next one is okay, but you need to keep track of what changed from one point to another point. And if you don't know what changed, the answer is, and most importantly, you need to know who changed and why they did the change, why the new samples were added to your data. if you don't have the answer to this, that's kind of scary. So what do we want? Usually, people in the industry, they want something that has a snapshot view of your data, something that can answer the question of who changed and what was changed, and also they want to know the common aspects for a particular data set. Now let's go back to Netflix. So remember all the examples I showed you. And what happens is that 2 years back, my manager came to me and said, you know, we want to build this. And you should make us a platform that will be managing all this data. Let's start from the beginning. You have a picture like this. What we can derive from here? Well, it's a movie. It's moving. So there is definitely a time dimension to it. And there is also a space. So we know that the Y is moving on the left, and there is this beautiful mountain on the right top. But you probably don't want to put any text on the left or on the other right, so you won't cover the important pieces of the picture. Similarly, there are those things flying, and you need to know where they're coming from. So somehow you don't want to cover that either, and all this information has to reside somewhere. So some details about how movie work. There is this thing called time. And then we show pictures in some succession, as well as we play sounds in some succession. And then in some other succession, we show the subtitles. So at least we need to be able to model that. With the data model that we'll be putting in place, this thing has to be fixed. Now the other part is the space. So it's going to be spatial temporal thing. You need to be encoding both those rectangles around the faces or any other objects of interest, as well as the time. And if you are on a shoestring budget, like you usually are with a new team, what do? Well, you function like a startup. You find the easiest way, easiest data structure to manage that. Essentially, you build everything with a duct tape. And I don't know what you think, but in my worldview, the duct tape data structure of programming is JavaScript. So our first idea was this. Well, not exactly that, this. So we had just a bunch of JavaScript saved in the Cassandra table, and we would just write to it. We would write both spatial and temporal information and just keep doing that. That didn't work that well. The problem? It's simple, it's great, but the danger comes from the fact that we're actually a microservice architecture. At Netflix, everything is a microservice. So microservices roughly look like this. Everything is moving all the time. You have no control over things. You can fix maybe an output of a single service and make sure that it conforms to some standards, but not the whole picture. So, okay, the next thing was, all right, we will not make everyone save the same thing. We'll make some people save their things, but we'll also be confirming the data and treat that as a snapshot of their view. Okay, so we got the snapshot. Now, another part is that because those are microservices, different services are owned by different teams. And different teams tend to have completely different ways of how they want to model their data structure. So eventually, after some time, it looked like this. You cannot make sense of all the different JSONs we had in a database. Eventually, what we had was some mess that we need to untangle. And the solution to that was a common data structure that we validated on the input. You can think of that as schema on the write as opposed to schema on the read. So when people save their data into the HBase or Cassandra or any other distributed hash table, they don't care about the structure they write, and then they take care of that when they read it. This creates a problem. If everyone writes different things, you exponentially explode the number of combinations that you need to resolve at the very end. And what we do, we actually have like a stop sign. Unless your data conforms to a specific standard that we declared, we won't let it in. There is still a flexibility. So it's all these 3 different requirements met in one place. First, it's flexible. At least there is a flexible part. Second, it presents you a snapshot view of the data. And third, there is a common aspect to it, which is roughly checked. It sounds crazy, I know. We're gonna taking the things from different places and mixing them together, but this is the thing that worked. So what happened in the end is we had a snapshot view, some way of snapshot view, we had a common format, and we had an API. Together, this thing gave us an answer to what changed between the moment A and the moment B. And we started gaining insights of what was happening to our metadata and how we would generate our data sets for various checks and various analyses. What does this mean in general? That's a profound question. I would say 2 things. If you are building your machine learning system, first, make sure that it's about data. Data itself is about the management and monitoring. Without monitoring, your management has no sense. When you are designing the data system, make sure that you know your problem. You're not solving someone else's problem. You're not solving the problem that some marketing department is pushing on you. Make sure you know your users and your particular constraints. Try to solve it in the simplest way possible. And then monitor your solution, talk to your users, and figure out what you want to change. Go to point 1 if you need to. And above all, if you forget everything else I was talking about here, make a picture of this book. It will not give you answers, but it will give you much more important thing. It will give you questions. You will know which questions to ask to your customers, to your users, and to your system. And by answering them, you will learn to build much better systems than before. All right, so much talk about the data and its management, but we started with the gradient descent and how it can be better. Let's go back and revisit that a little bit. So what I believe might be happening as we speak is that previously we had a system where we were writing everything in pure, complete code. The code was doing something, it was doing exactly the thing that we told it to. Sometimes I wouldn't understand what the code was doing, but anyways, the code would do just what I told it to. Now, it seems that in most cases where you have a code that has lots of rules, lots of if statements, switch cases, places where you are trying to make a conclusion from some collection of inputs, they could be replaced with a function approximation. And function approximations work much better than us at figuring out the particular rules. So it is possible that in the world of tomorrow, instead of writing code in C or Java or whatever, we'll be writing code that manages the data, which describes the problem. And once that problem is completely defined, or at least defined in some shape or form, we'll let the gradient descent figure out the optimal solution for us. And that's my last takeaway for today. Thank you. I'll try to go to questions. I was told to check out some new fancy app. The first one seems to be, when will The Witcher come out? I wish I knew. How to improve performance of the Netflix conductor? Great one, great one. So there are several things. First of all, Netflix conductor is a workflow orchestration system that we actually employ ourselves. And if you want to use it, make sure that you have the right underpinning for it, that you are using the right database. Dynamo seems to be working fine within single data center, cross data centers. It gets much more trickier. Talk to me about that after, because it can be a really, really long conversation. I think I answered the second one. The third one, what is Netflix conductor? Now, how such attacks determine internal algorithm of neural network in case of black box attack? That's nice. So it seems that there is no need to determine the weights of a neural network. If your statistical model happens to be a neural network and it's being attacked as a black box, the only thing you need to know is how much your categorization differs every time you change some part of the input. So you can start by modifying maybe smaller blocks, smaller macro blocks on your picture by some amount, and then measure how much the confidence is changing. I'm quite doubtful that you'll be able to, with the black box attack, make neural network predict some particular class that the attacker wants to predict, but it's possible to change the perception of some class to some different one. What tools and/or platforms are you using at Netflix for dataset management? So that's the beauty of the art. We're just building that. NMDB might become one, and we're still hypothesizing and thinking of some more. Overall, the dataset management and the data management itself is a quite novel field right now. How to convince other departments to use the common model. You come to them with a big smile and a gun in your hand. No, frankly speaking, there has to be a value. There has to be a value in what you're offering, and oftentimes the value is that once you take care of their data, they're not responsible for it. Their data will live with you long after their service is gone, long after the person who created the service is gone from the company. So it's freedom from their future headache. This point sells really well, in my personal experience.
Ще раз подякуємо нашому спікеру Арсену Костенку за дуже чудову доповідь.